Text, Indeed. 1 search. All jobs. At Indeed ENG. Title, Machine Learning at Indeed. Scaling decision trees.
Welcome to the 11th Tech Talk here at Indeed. I'm going to talk about machine learning here at Indeed, and specifically decision trees and how we scale them to extremely large data sets. Once again, I'm Andrew Hudson. I'm the Chief Technical Officer at Indeed, and I help people get jobs. Indeed is a search engine for jobs. We write programs that crawl the web. We crawl tens of thousands of job sites. We gather all this information into one place so you can simultaneously search all of those sites and search the jobs from those sites in one place. It's very much like Google, but just specifically for the job vertical.
Job search results page.
This is a very normal job search results page on Indeed. As you can see, there are 4 jobs on this page.
Patient Services Representative, After-School Staff, Workforce Coordinator, Texas Works Advisor 1.
This user is querying, actually there is no query. He just left the what field blank and looking for all the jobs in Austin, Texas. This is what we call at Indeed a blank query or a location-only query. This is a very common query on our site. A lot of job seekers, they don't really know exactly what they're looking for. We're actually very good at this query, and we're very excited about that. Big problem, though, is which jobs do you show for this query? You may not have noticed on this page, but there are actually 18,749 jobs that match this query. If a job seeker were to spend their time looking through every single one of these jobs nonstop, we estimate it would take about 72 hours for them to look through them all. And meanwhile, 1,500 new jobs would arrive to the site that match this query. So it's very important to figure out what are the best jobs we can show them to save them a lot of time in their search. So we're here to help people find jobs. So let's show the jobs that maximize the chances of them getting a job.
Which jobs to show? Maximize job seekers' chance to get the job.
We break this into 4 subproblems. Will the job seeker click on this job if we show it to them? If they don't click on it, it seems highly likely they're not going to get the job. Is this job even still available? On this third-party site, is it now expired, or is it really old and unlikely to still be actively hired for? Let's say they click on the job. Will they actually apply to the job? If they don't apply to it once again, they're not going to get the job. Are they even remotely qualified for this job? Are they just going to add their application to a whole stack and they're just going to be thrown away immediately? This is another important problem for us. This is kind of the state of the art for us, actually, that we're working on right now. Today, I'm just going to focus on will the job seeker click on the job if we show it to them.
How?
So to do that, we're going to log all of the jobs that we show our job seekers. We're going to log everything that we can about that job seeker, what query they did, all the typical stuff that you do on the web. We analyze those logs, and we look for patterns for what best explains which of these jobs they clicked on, what are the patterns for the jobs they didn't click on, and we want to leverage that information to predict for future job searches and future jobs that come to our site, what's the probability they're going to be clicked on by these users? This process is very common in machine learning. It's called a supervised learning problem. In this case, the job seekers are supervising our machines. They're telling it, these are the good things you showed me, these are the bad things you showed me by not clicking on them. And the machines are just going to learn from this information. And we get tons of this information every single day. There are a lot of different approaches you can take to supervised learning problems.
Supervised learning approaches. Neural networks, genetic programming, support vector machines, bagging, Bayesian methods, logistic model tree, random forests, regression, decision trees, nearest neighbor, boosting, and ensemble methods.
I've put 12 of them on this slide. Various techniques and approaches, algorithms. I'm just going to talk about decision trees today. One nice thing about decision trees is you can actually first run your data through a decision tree algorithm, and then you can apply any one of these algorithms to the pieces that are left over from that. Additionally, it's often used as a building block in these algorithms in a more direct way.
What is a decision tree?
What is a decision tree? Decision tree is a tree-like structure that presents a relevant sequence of questions that are going to guide you down a path through this tree until you reach some outcome or prediction. Let me show you an example. So around the office, I saw that there was this sheet of paper on the refrigerator entitled, "I'm thinking about buying a laptop." Turns out this is a decision tree. First question I ask you, is quality important? If the answer is no, then you should buy an Asus laptop.
An arrow from question to Asus.
Or whatever Woot has. If the answer is yes, do you want to run Linux on this laptop? If the answer is no, you should get a MacBook. And if the answer is yes, you should get a Lenovo laptop. There were a few other options on it as well.
Is quality important? If IDGAF, then get a Dell. Want to run Linux? If hell yes, then get System 76.
What are some benefits of using decision trees? Well, by the end of this talk, you'll understand them very well. You'll see that they're actually quite simple to understand. And the end product of a decision tree, the model, is also very understandable. You can look through it. You can see what decisions, what paths it decided to take. You can investigate those, see if maybe there was a better path it could have taken, and tweak it. We really like them here at Indeed.
Decision tree learning.
So I'm going to talk about the programmatic creation of decision trees. The decision tree I showed you earlier was just built manually by someone. It's just their subjective thoughts on the matter. But if you had a large amount of data on what laptops people bought, how they liked them, what are some of the things they considered, you could build one of these trees just straight off of that data. So the process of building one of these trees is you start with all the data you have. I'm going to call them documents. And you find a way to split it into pieces that optimize some criteria. Then you're going to repeatedly do that for each of those pieces that are left over until you're down to something that you can't split up more, or you just do this some number of iterations. I'm going to go through an example.
Titanic example.
I'm going to use data from the Titanic. I'm sure everyone here is aware of the Titanic. It was a very large cruise ship, the largest at its time. It's actually quite small nowadays. And it sunk on its maiden voyage. There's even been an Oscar-winning movie made about this that you may have seen. On the ship, there were 1,300 passengers, but only 500 survivors. So that's a 38% survival rate. Maybe we can use a decision tree to discover what best predicted who would survive and who would not in this tragedy.
What best explains who survived?
We're going to look at just 3 characteristics of the passengers. First, we're going to look at the ticket class. There were 3 classes of tickets. There was first class, second class, third class. We're going to let family size, I'm going to abbreviate it as F size. So that's the number of family members you had on board. If you were just by yourself, that'd be 0. If you had your wife and a child, that would be 2. And we're also going to look at the gender of the passenger. So this cloud here, imagine this is all of the passengers on the Titanic. 1,300 passengers, 500 survivors. First, let's look at the first class passengers.
A purple cloud within the larger green cloud reads, class equal 1.
There were 323 of these passengers. 200 of them survived. It's a 62% survival rate. That's much better than the global average. We can easily get statistics for everyone who wasn't in first class. We just subtract these numbers from the total.
Class does not equal 1. 986 passengers. 300 survivors. 30.4% survival.
And in that case, you only had a 30% survival rate, much lower than the general average, and a pretty big difference between these 2 groups. So maybe this would be the first thing you would want to consider when predicting who would survive. But we're going to try a lot of different ways for splitting this data up. So we need some sort of way to score this split. For this example, I'm going to use conditional entropy.
Score. Conditional entropy.
I've put the full expanded formula for that on the board here. I'm not going to go into details on that. But the spirit of conditional entropy is if you know some additional piece of information, it helps reduce the uncertainty about a prediction. So in this case, we want to find things that have lower conditional entropy because it's less uncertain. We run that data through that formula, and we get 0.6267. What does that mean? Well, it's actually not that important, but it's the best thing that we found. So we're going to keep it. And now we're going to try more things.
Class is less than or equal to 2.
What if we combine first and second class? 600 passengers, 319 survivors, 53% survival rate. So it's a slightly lower survival rate than just first class.
Class is greater than 2. 709 passengers, 181 survivors, 25.5% survival.
Everyone who's not in first and second class, in this case those are all the third class passengers, run it through the formula and we get a score of 0.6244. So remember, conditional entropy lower is better. That's slightly lower than what we had before, so we're going to remember this split and just forget about the old one. Like I said, third class passengers, we could consider them by themselves as well.
Class does not equal 3. 600 passengers, 319 survivors, 53.2% survival. Class equals 3. 709 passengers, 181 survivors, 25.5% survival.
And in that case, it's just the symmetric, the inverse of the previous split, and it actually gets the same exact score as you would expect. It doesn't really help you decrease the uncertainty of the future. Let's look at the women passengers.
Gender equals female.
There were 466 of them on board, 339 survivors, which is roughly 73% survival rate. That's even better than first class.
Gender does not equal female.
The men on board, 843 of them, 161 survivors, 20% survival rate, so much lower than the general population. Intuitively, this feels like a better way, the more important factor. What does the score say? 0.5525, so that's lower. So we're going to keep this as our new best split. Just going to look at one more. This is family size. If you had no family on board, that hurt your chances of survival, 30% survival rate. If you had some family, it helped your survival rate.
F size does not equal 0. 519 passengers, 261 survivors, 50.3% survival. F size equals 0. 790 passengers, 239 survivors, 30.3 survival.
But the score is not nearly as good as gender. It's similar to first class. So the next step, we found the best split. So we're going to segment the data.
The cloud separates into two smaller clouds. The blue cloud is 19.1%, pink is 72.7% survival.
So in the upper left, I have the men at a 19% survival rate, and the women in the lower right, 73%. And we're going to repeat this process on each of these separately. I'm just going to look at the men next.
Gender equals male. 843 passengers, 161 survivors, 19.1% survival.
Once again, 843 men, 19% survival.
Class equals 1. 179 passengers, 61 survivors, 34.1% survival.
First class. Men who were in first class, 179, 61 survivors, 34% survival. So first class still helped your chances as a man.
Class does not equal 1. 664 passengers, 100 survivors, 15.1% survival.
Every man who wasn't first class, 15% survival rate, gets a score of 0.47. That turns out to be the best way to split this. So we're going to repeat this process. We're going to segment the data here. And we just repeat this process and so on. At the end of this, you built a tree-like structure. You started with all the passengers at the top. They had a 38% survival rate. Separated the men and the women.
19.1% male and 72.7% female.
Just looking at the men, we separated first class from not first class.
15.1% not from first class and 34.1% from first class.
And you repeat this process.
Male. Class size does not equal 1. 13.1% family size does not equal 2 and 33.9% family size equals 2. Female. 49.1% class is greater than 2 and 93.2% class S less than 2. Class is greater than or equal to 2. 24.4% with family size greater than 2 and 54.9% with family size less than or equal to 2.
So the category that had the least survival rate was men who were in first class who didn't have exactly 2 family members. And the highest survival rate was women who were in either first or second class with a very high 93% survival rate. So what does this have to do with the problem of predicting which jobs users are going to click on? Well, it actually turns out it's the same exact problem in a different form.
Predicting click probabilities.
Consider the passenger's impressions on these jobs, meaning we showed that job to that user. And the clicks, those are the jobs that survive that process.
For each candidate job, follow path through tree, then take click through rate of terminal node.
Once we build a decision tree using that data, if we want to give a job a score to predict whether it would be clicked on or not, all we have to do is follow the characteristics of that job through a tree until we figure out what its click-through rate was. I have an example of that here. So this is something I handmade, actually, but using data from our internal analytics tools.
Simplified decision tree for query equals sales.
And I just looked at data for the query sales. This is the 10th most popular query on our site. And I only looked at what are the words that appeared in the job title. So to score a job for this query, you would start in the upper left, and you would ask yourself, does it have the word sales in the job title? And if the answer is yes, you would move down and repeat that process. The next question would be, does it have the word representative in the job title? And so on. If it didn't have the word sales in the job title, you would move right and ask, does it have the word account in the job title? And if it does, then you move down, great, you're finished. You landed at a score of 3.8%.
Job title equals sales representative.
So some examples, say you have the title sales representative, has the word sales in it, so you move down, has the word representative in it, move down again, doesn't have the word outside in it, doesn't have the word service in it, doesn't have the word inside in it, and all of the data that matched this pattern had an overall click-through rate of 4.6%. Another example, account executive.
Job title equals account executive.
Start at the beginning again, doesn't have the word sales in it, does have the word account in it, go down and you're done, 3.8%. That's not a bad score for not even having the word sales in the job title. Turns out that's basically a synonym for a salesperson typically.
Job title equals outside sales representative.
Outside sales, just all yeses straight down, 5.1%. That's actually the highest score on the board here.
Job title equals sales associate. It has the word sales and associate, but not representative and manager.
Sales associate, 1.8%. It's more like a retail job. It's not really what job seekers are looking for when they do that query.
Job title equals inside sales representative.
Inside sales, 4.4%. Seems like job seekers on our site prefer outside sales over inside sales. Sales manager, slightly lower score. A lot of them aren't maybe interested in management. They just want to be a sales guy, etc. Store manager, also another retail-like position, pretty low click-through rate.
Final CTR predictions.
So you just run each of the job titles through this tree and you get a score. This is the final ranking for those job titles. If this was the only ranking factor that we used, for that query, every job that had outside sales representative, it would outrank any job that doesn't have that job title or any of these other job titles. But it's not the only ranking factor we use. But it's the only one I'm talking about today. So how are we going to write a program that does this? I'm going to start with a single machine implementation. This is actually an implementation that we came up with about 7 years ago, and we've iterated from there and evolved it. Quick overview of what we're going to do here.
Tree building strategies.
So in general, when you're building a tree, there are two well-known strategies. There's depth-first strategy and a breadth-first strategy. I'll explain these.
An oval with the number 1 with 2 arrows that point down to 2 and 3.
Depth-first means you're going to start with all your data at the top here. You're going to find a way to split it up. And you're just going to go to the left and repeat that process.
2 arrows point down from 2 to 4 and 5.
You're going to go to the left again and repeat that process. So you're getting deeper and deeper.
Arrows from 4 point to 6 and 7.
Repeat that process. Then you're going to come back up. You're going to start picking up what you missed on the way down. Suppose group 5 here, there was nothing that we really liked for splitting it up, so we just terminate there. And then we go to group 3, and so on.
Arrows from 3 point down to 8 and 9.
The breadth-first strategy is we do this one level at a time from left to right. So first we break up the first group into 2 and 3. We break up group 2 into 4 and 5, group 3 into 6 and 7, etc. Just from left to right. Once again, group 5, we didn't find any way to break that up that we liked. There's actually another way to build trees. This is what I'm calling one layer at a time, all nodes at the same time. So we have all the data here. We're going to iterate over all the data, and we're going to evaluate every possible way of breaking this up, and then we're going to apply that.
A dotted line between 1 and the arrows that point down to 2 and 3.
Then we're going to iterate over all the data again, and we're simultaneously going to evaluate every way of breaking up group 2 and group 3, all mixed together.
Dotted line below 2 and 3.
And then when we're done with that, we're going to break those up. And we're going to repeat this process. Now in group 5, in this case, we're just going to move it to this logical group 0 so that we ignore it on future iterations. And you repeat that process some number of times or until you can't find any way to break them up any further.
Data format.
So let's look at the Titanic data. This is a typical way that people look at data. It's a tabular format. We've got columns, we've got rows. In this case, the columns are passenger ID, the class, the family size, gender, and whether they survived or not. And each of the columns is the data, first one, or each of the rows is the data for each passenger. So the first thing we're going to do is we're going to tear this up and throw it away and create an inverted index. This is really the key to actually doing this algorithm efficiently. So an inverted index is much like the index on the back of a book. So it maps words or terms or concepts to which pages in that book contain that word or term or concept. And then those terms are stored in sorted order, so you can quickly find the term you're interested in. The pages are usually stored in sorted order. You can get an idea of where in the book that page is. We love inverted indexes here. These are actually the core data structure that makes search engines possible. And all of search engine algorithms rely on this data structure. So here's that data structure for the Titanic data. We have the field. We have the different terms that that field can take on. So in this case, it was first class, second class, and third class. Then we have a list of the documents of the passengers that are in first class, second class, and third class. So you can see those are in sorted order, and actually they're sequential in this case because my data set was sorted by class. Family size. You can see now that the documents are more jumbled, but we still have every passenger represented by what the size of their family is. Gender, and whether they survived or not. Implementing inverted indexes is not terribly simple. There's an open source implementation called Lucene that's widely used. We use it very widely inside Indeed. It has some downsides. So we actually wrote another one called Flamdex that we use internally, especially for large, very, very large data sets. But I would recommend, if you want to work with inverted indexes, you just pick up Lucene.
Primary lookup tables.
So before I go into the pseudocode for this, we need a little bit of preparation. We need a fast way to look up where each of these passengers are in this tree that we're building. We're going to call that the group lookup table. It's initialized to all ones, because remember, all the passengers start at the top together. We also need a way to quickly look up the value we're trying to predict, which in this case is whether they survived or not. We can actually construct this values array off of that inverted index so that we don't have to keep multiple data formats. But that's a topic for a future talk.
Main loop overview.
Here's the main loop. We're going to iterate over each field in this inverted index. We're going to iterate over each term within that field. We're going to get some statistics about how well that field and term split up each of the groups we're currently considering. As we're doing that, we're going to evaluate those splits and retain the best way of splitting it up. And then we're going to apply those splits. And we're just going to repeat that process.
Main loop first iteration.
So for the Titanic data, first iteration, we're going to iterate over class, followed by family size, followed by gender. The different values that class can take on, first class, second class, third class. And we're going to get statistics about how well each of those split up group 1 on the first iteration. For get group stats, we need a couple more arrays to keep track of these statistics. We're going to keep a count of how many documents we've seen in that group for that specific term. And we're going to keep a running summation for whatever value we're trying to predict for that term and that group. So these are both initialized to 0.
Get group stats.
So getting group stats, for the current field and term, we're going to iterate over each document that contains that field and term. We're going to look up its group. If it's 0, we're just going to skip it. And we're going to add up our statistics about this field term group pair. So for the Titanic data, we're going to look at first class first. These are the different passengers who are in first class. These are the groups that those passengers are currently in. And this is whether those passengers survived or not. So we're going to step through this data, start with a count of group 1 having 0 passengers, 0 survivors, and just step through it one document at a time. We look up its group. It's in group 1. So we increment the count for group 1. The passenger 0 survived, so we're going to increment vsum. So for passenger 1, they also survived, so we increment vsum, and we also increment the count. Passenger 2 did not survive, so we don't increment vsum.
Highlights each number as he lists them.
Passenger 3 did not survive. Passenger 4 did not survive. Passenger 5 did survive. So at the end of this, we have the statistics that we saw before, which is 323 passengers and 200 survivors who were in first class.
The purple cloud within the green cloud labeled Group 1.
So once again, all these documents are in Group 1. We're going to consider all of the documents in Group 1 that are also in first class. Count of 1 is going to be the number of passengers, and the vsum of 1 is going to be the number of survivors.
Get group stats.
For class 2, you can see the results of that here.
Count 1 equals 277, vsum 1 equals 119.
In class 3, you can see the results of that here at the bottom.
Class 3, 709 and 181. Main loop first iteration.
So we have a way to get statistics about how well each of these, or the statistics of what would happen if we use this term to split up these groups. Now we need to evaluate them.
Evaluate splits.
So first we're going to check if the split is admissible. That's basically, does the split make sense? Do we really want to use this for predictive purposes? There's also some engineering concerns here. It may be that the split is very significant, very useful, but it's a very tiny percentage of your data, and you might end up building these very weird, lopsided trees. So you might do a balance check to see, maybe you would only do it if it's more than 1% of your data. Additionally, you don't want to just build a predictive model on noise, so you also do a significance check. In this case, since it's a Boolean prediction, use something like a chi-squared significance check. You're going to score it if it passes the admissibility test. And like I said earlier, we're using conditional entropy, but you can actually use a lot of different ways of scoring this split. And we're going to retain the best scoring split as we go along. So to evaluate the splits, we're going to need a little bit more information, more arrays. We need a total count of how many documents are currently in each group, because we're going to subtract from that to get everyone who's not in the current field and term. Need the total value. So in this case, it's first iteration, we only have one group. Total value would be about 1,300 passengers, or total count would be 1,300. Total value would be however many survivors. We also need to keep track of the best split for each group as we go along. So we're going to just initialize best split group to all nulls, and we're also going to keep the score of that split so we can check if each split is better than what we had before. And the loop to do this looks something like this. So we've gotten statistics for each of these group and for the current field and term. Just check if it's admissible. If it's not admissible, skip over it. Grab the score for it. In this case, we're using conditional entropy. And if that score is better than the current best score we have for that group, then we retain that split and retain that score.
Main loop first iteration.
So after the first iteration, we've discovered that the best split is gender equal female. And now we need to apply that split.
Apply best split.
So we're going to encode each split as a combination of a target group. So that's a target that we're going to use to split up, this term to split up. A positive destination group, so if the documents, all the documents in that target group that match this condition, and a negative destination group. So in this example, we're targeting group 1. The condition is that you're female. We're going to find all the female passengers that are in group 1, and we're going to move them to group 3. And then we're going to do a cleanup pass to move everything in group 1 that's left over into group 2, because they're the non-females, in this case the males. And then there's nothing left in group 1. So we're going to use that inverted index again to do this. So we're just going to look up the term gender equal female in that index, iterate over each of their docs, check if they're in the current target group. If they are, great, move them to the positive destination. Otherwise, we're going to move them to the negative group later. So in this example, this is what that looks like. So passenger 0 is female. She's currently in group 1, and we're going to move her to group 3. Passenger 2 is currently in group 1. They're going to move them to passenger group 3, and so on. As you can see, we have all these 1s left over. We're going to just move them all to group 2.
Main loop.
And we just repeat this process.
Red oval labeled 1.
So after the first iteration, we iterated over all the possible ways we could split up group 1.
Dotted line under 1.
Discovered that gender being female is the best way of breaking that up. We applied that split, and now we're left with group 2 and group 3.
1 turns gray.
And now we're going to go into iteration 2.
Main loop second iteration.
It's a little bit more interesting this time. Let's look at first class to start with.
Get group stats.
Now all the first class passengers are now mixed between groups 2 and group 3. So all the first class passengers that were male are in group 2. All the first class passengers that are female are in group 3. And at the end of this, we have 2 separate counts and statistics. And we just build them up piece by piece as we iterate through this data. So now we have a count of how many first class males there were, how many of them survived,
179, 61.
and how many first class females there were and how many of them survived. And you can see that's a very high survival rate for the females here in group 3.
144, 139.
Same thing for class 2. At the bottom here, you can see the statistics for second class passengers who were male and second class passengers who were female in group 2 and 3.
Male, 171, 25. Female, 106, 94.
Same thing for third class. At the bottom, you can see those statistics.
493, 75. 216, 106.
When we get to the term female, it's a little odd because actually all of the documents are in group 3 that are female. In that case, we don't have any data for group 2.
0, 0. 467, 339.
And this split would just be considered inadmissible, and we would just skip over it. And this is the analog for gender male.
844, 161. What about inequality splits?
So earlier, we actually used an inequality split in my clouds. How do we add that to this algorithm?
Main loop plus inequality splits.
Well, every time we start a new field, we reset some statistics that we're going to keep track of for evaluating inequalities. And we're going to keep a running summation of all the terms. And since the terms are in sorted order, we have statistics about everything that's less than or equal to the current term for each group. And we also add those to our evaluation.
Scalability.
How does this algorithm scale? We find that this actually performs very well on a single machine. We iterate on it a lot. We've got to actually quite large data sets on a single machine. But at some point, we started to hit limits. We wanted to apply it to larger and larger and larger data sets. So we started thinking about how do we go to multiple machines.
Multiple machine implementation.
When thinking about multiple machine implementations, the first thing that may come to mind is Hadoop. It's an open source technology that implements a MapReduce paradigm.
Hadoop.
We tried this. Turns out that to build each one of those levels, it takes 5 or 6 MapReduce jobs. And kicking off each one of those has a pretty high latency of 30 seconds to 2 minutes. So you're already looking at 5 to 10 minutes overhead just for each level. And we found that this process was actually much slower than even using a single machine, because Hadoop behind the scenes is constantly writing data, intermediate data to disk. It's shuffling data between all your machines. So we ultimately shelved this, and we learned that Hadoop is not great for iterative algorithms. We're just going to iterate over the same data repeatedly. So we had to make our own solution for this.
Partition data.
Well, the simplest thing for building a distributed algorithm would be, well, let's first start by partitioning the data. And if we can put it on 2 machines and figure out how to leverage both those machines to do the same thing, then we're in good shape. So we took our inverted index, just break it in half, however you want.
A triangle labeled inverted index split in 2.
This is called horizontal partitioning. So some documents are going to go one way, some documents are going to go the other. And then we have 2 shards.
A new smaller triangle from each piece.
We're going to put each of them on their own machine. How can we do this Same algorithm now. We had the data spread across two different machines. Let's go back to the main loop, starting with the first 3 lines. So we want to iterate over each field, each term, and get some statistic about those groups. This is what we call FTGS, and we use this acronym all the time when talking about decision trees, because that's each field, each term, and the group stats. If you were to add a print line after this loop and just print out the field, the term, and the statistics for each group, it looks something like this.
FTGS stream single machine. Class equals 1, 1, 323, 200. Class equals 2, 1, 277, 119. Class equals 3, 1, 709, 181. The stream gets narrower.
This is all the information we need to evaluate the best splits for each iteration. We've got the field.
Class equals 1.
We've got the group.
1.
And we've got the statistics for the current group.
323, 200.
And these are all in sorted order, starting with the field, then the term, and then the group. And this is what it looks like for the Titanic data.
Scrolls through the data stream.
Great. If we can just build that, if we can just get that information, then we're good. We have all the information we need. How are we going to do that across 2 machines? Well, we can independently initiate this FTGS stream from machine 1 and from machine 2. It's 2 separate sets of data. It doesn't give us the complete picture. But you can actually merge these together on a 3rd machine quite easily, just reading this information over the network and merging it together into a new stream.
FTGS stream merge.
So let's say this is the data from machine 1, and this is its FTGS stream. And this is the data from machine 2. As you can see, they're different now. And we just start looking at the first thing that's coming from machine 1 and the first thing that's coming from machine 2. And in this case, we see they have the same field, the same term, and the same group. So great, we can just add those together. And now we have the original global stream, the first element of that. Move each of those forward. In this case, there's a little bit of a problem. For machine 1, we have data for class 2 and group 1. But for machine 2, we only have data for class 3 and group 1. However, since these streams are in sorted order, we know that there is no data on machine 2 for class 2, group 1. And in that case, we just take the data from machine 2, and we only use that. And you move that forward. Now they're aligned again. So we just merge them together, just add them up. We've got the global value for 3rd class in group 1. Now we have another alignment problem. This time it's family size 0 from machine 1, family size 1 from machine 2. Since they're in sorted order, we know that family size 0 doesn't exist on machine 2. So we just take the data from machine 1. And you repeat this process, and ultimately you rebuild that original global FTGS stream. So great, that works for 2 shards. But what about 6 shards?
6 triangles with arrows pointing up.
We can start an FTGS stream for each of them. And with a slight change to that previous algorithm, you can actually merge all of them together all at once. And that's called a Kway merge. Also a common algorithm found in search engines.
FTGS 1 through 6.
And now we have the complete FTGS for shards 1 through 6.
6 triangles inside each of 3 larger triangles.
And you can nest this pattern. So suppose we have 18 shards of information, and we have 6 on each of these 3 machines. We can first create a local FTGS stream on each of those machines from those shards, transmit them over the network to another machine. That can merge those streams together, and now it's produced the FTGS streams for all 18 of those shards. You can nest this again. Say you have 36 shards, and we have 2 additional merge points. And we recreate the global stream for all 36 shards.
Main loop FTGS.
Great, so that takes care of FTGS. Now all we have to do is evaluate this data that's being streamed through us. This is actually very easy to distribute. It's just wherever you're merging this data, you just evaluate the data as it's coming in, It's actually quick to evaluate it. It's much harder to merge that information together than it is to evaluate it. So no problem there. But we still have to find some way to apply these splits.
Regroup.
And this is what we call a regroup operation. So back to the previous scenario, we've merged these 18 shards together, created this FTGS stream. We evaluated all the data coming on that stream and found the best splits. Now all we have to do is push that information down back to those machines.
Arrows point down from top to the original 18 triangles.
Each machine is going to send that command down to each of its shards, and it's going to apply it to each shard in parallel. And we're just going to wait for that to finish.
Arrows flip and all face up.
And once that's finished, well, now we can start on the next iteration of the algorithm. When we're done with that, we just push new regroup commands down. You just oscillate between these until you've built the entire tree.
The arrows switch between up and down.
So we've built this system. We call it MUTEP. And you can think of MUTEP as a distributed system that does efficient FTGS and regroup operations on inverted indexes. This cluster of machines right now that we're operating on has 32 machines in it. Each machine has 2 CPUs and 6 cores on it, 128 gigabytes of RAM, and 10 1 terabyte drives. So that entire cluster combined has 384 cores, 4 terabytes of RAM, and 320 terabytes of disk. So let's look at a very big decision tree and building it on top of this hardware. So let's say we want to build a decision tree on 13 billion documents. In this case, these documents represent impressions on jobs and whether they were clicked on or not, and data associated with those impressions. By storing this in an inverted index, it actually isn't terribly large. It's only 330 gigabytes. That's only 25 bytes per impression on our site. It's kind of magical. It's a nice feature of inverted indexes. They also greatly compress your data for you. So let's say we're going to do the first FTGS pass on this data. We timed this. It takes 314 seconds. And during that process, we evaluated 36 million distinct terms. And we found the terms that work the best. And then we're going to apply that regroup operation, which takes 9.6 seconds. In this case, we actually don't just split one group at a time. What I described so far was just doing one split at a time, but you can actually do multiple splits. And for this build, we ended up building 7 groups. And then the second iteration on that data, 57 seconds, so that's quite a bit faster than in the first iteration. The first iteration was loading a lot of that information into RAM, into the disk cache on those machines, and now the second iteration is much faster. And that data is just hot in RAM. And we push that regroup operation down, takes 23 seconds, and we have a total of 217 groups after 2 iterations on this data. As you can imagine, the number of groups grows very, very quickly. I think we usually hit up to 1 million groups simultaneously. However, this is great for building decision trees, but it is also great as a general analytics platform. It turns out that a lot of important, interesting business and product questions decompose into FTGS and regroup operations. For example, if you want to know the top 10 queries being done on the site, that's like an FTGS operation. You just get data for all the queries on an FTGS stream, keep track of the best 10 as you're going along, and then at the end of that, you've got the best 10. So you want to graph how many searches are being done hour by hour. That's like a regroup operation. You just have to regroup your data into groups that are hour by hour. And we're going to go into a lot more detail on that in the future Tech Talk. There's also a lot more you can do with this platform. We've expanded it to do linear regression and logistic regression, and we have plans to push more common machine learning algorithms into these abstractions. Next Tech Talk, we're going to talk a lot more about how the system works. We're going to talk about how we shard data, how we manage those shards, figuring out which machines to put them on. What's the protocol for talking to this data? How are we going to send this FTGS data over a network efficiently? How are we going to manage memory? This is a common piece of infrastructure used by a lot of people within Indeed simultaneously. We don't want anybody to be able to take it down. How do these inverted indexes do so well? What are the tricks used in that? How do we efficiently do these FTGS merge operations and efficiently do these regroup operations? And then how do we tolerate a machine failing?
Conclusion.
So in conclusion, we now have a system that can scale arbitrarily. If we wanted to build a decision tree on 40 billion documents, well, maybe we just need twice as much hardware, and it'll still take roughly the same amount of time to finish. This has allowed us to increase the freshness of our builds. So we build our models more than once a day, ship them to production, and how many different models we can build. So we can end up tweaking these models and evaluating them and use them as part of A/B tests. It's not uncommon for us to get 1% gains week over week over week just by tuning some parameters in a decision tree or in some other machine learning algorithm.
Continuous improvement graph.
If you look at just our sponsored job click-through rate from November 2012 to November 2013, it's increased by a staggering 84%. Thank you.
Logo, Indeed. One search, all jobs.